All right, this is a question from our module on equilibrium material. So we have this chemical reaction. We have a solid producing two products, and each of both the products are gases. I have a total pressure of the gases at equilibrium, and I'm trying to find the equilibrium constant K sub P for the reaction. Let's go ahead and write the formula for the K sub P. All right. The equilibrium constant is products over reactants raised to the stoichiometric coefficients. If we're doing this in terms of pressures, then I only include the gases. I would never include a solid in an equilibrium constant anyway. And so this is the partial pressure of ammonia times the partial pressure of H2S. Remember, if there had been a balancing coefficient on either of those, then that would be the exponent. For example, if there were two NH3s in the balanced reaction, then my partial pressure of NH3 would be squared, and so on. So that's the formula for the equilibrium constant that I'm going to need to plug into. So I need the pressures of both NH3 and H2S at equilibrium. Now, I may not need an ice table for this. It may be too simple, but I think it does help us see what's going on. So I am going to set up an ice table. Again, this may be a little bit of overkill, but if it helps you see what's going on, that's good. Now, I'm setting this up in terms of pressures, not in terms of concentrations. And the pressure of that solid is meaningless, so I'm not going to put anything in this column. I don't need to. Initially, the pressures of these two gases is 0 because I don't have any, but the pressure increases. It changes as the reaction proceeds. I don't know by how much, but I do know that each one changes by the same amount, so I can use plus X for each of those, which means at equilibrium, I am representing the pressure of each of those gases as X. I also know, because they're each X, that the partial pressure of ammonia is equal to the partial pressure of H2S, and that's based on the stoichiometry. Again, if there had been a balancing coefficient, I would take it into account here. There might be a 2x or a 3x or something. Now I'm going to go back to what I learned from Gen Chem 1. And from Gen Chem 1, we learned about Dalton's law of partial pressures. And if I have more than one gas in a container, the partial pressure of the gases added together equals the total pressure in the container. And I know that the total pressure at equilibrium is 0.658 atmospheres. So the total pressure is 0.658. And the total pressure is made up of adding together these pressures, which are equal to each other. So that's like saying, well, 0.658 atmospheres is 2x, or x times x, or x plus x, sorry, it's x plus x, 2x. Each of those contributes x, add them together. This is x plus x, because it's these two added together. And so the pressure of each gas is 0.658 divided by 2. You should be plugging this in as I do, just to make sure, number one, mainly, that I don't make a mistake. But I get 0.329 atmospheres for each of those x's, which means the partial pressure of ammonia is 0.329 atmospheres, and the partial pressure of H2S is 0.39 atmospheres. So I can come back up and plug into this equation. So it's essentially 0.329 squared, or 0.329 times 0.329. Again, plug that into your calculator, and I get 0.10824 ... So the equilibrium constant, the K sub P, is 0.108.